I'm Won-Young Kim at Columbia University. I and my colleague, Professor Paul Richard, have been working on determining body weight magnitude of the 6 underground nuclear tests conducted by North Korea. Our ultimate goal is to stop nuclear weapons tests by any nation, since nuclear weapons testing is a crucial step in designing nuclear weapons systems. If we can curb the nuclear weapons testing, then we can effectively stop building nuclear weapons. Our work supports the Comprehensive Nuclear Test Treaty. On September 1996, the General Assembly of the United Nations endorsed the treaty by a 158-3 vote. The treaty bans all nuclear test explosions of any size. The CTBT organization is set up in Vienna, Austria, and is functioning in full capacity with an international data center and international monitoring system also nearly completed. Ultimate goal of NNSA is the nuclear weapons non-proliferation, and our research objective is to stop nuclear weapons testing. Hence, both have the same goal, but we work under the Comprehensive Nuclear Test Ban Treaty to achieve the goal. To verify the compliance of the treaty, the international monitoring system uses 4 major technologies for various test environments, as listed in the table on the left. 4 technologies are seismic, hydroacoustic, infrasound, and radionuclide, and the environments are underwater, underground, atmosphere, and near space. Here in the table, the P indicates primary technology used in a given environment, and S indicate secondary technology used for that environment. Map on the right shows various technologies and about 360 IMS sites deployed worldwide. The seismic, infrasound, and radionuclide stations are on land, obviously, and hydroacoustic sensors are in the ocean. In this research, we are specifically working on the seismic method. So here on the map, the primary and auxiliary seismic stations and arrays indicated by red circles. The body weight magnitude MB of an underground nuclear test at each station is given by a simple formula. The observed P wave amplitude is compensated for effective distance with function here B, and station side effect S, and regional wave propagation path effect here given as F. So all this compensation is needed. Each item in the equation needs careful assessment for a reliable magnitude measurement. Magnitude is in logarithmic scale, and usually it's a robust quantity for both earthquakes. For UNTs, we require a more reliable estimate because we are going to use the magnitude to estimate the yield of an earth explosive. Here, the event magnitude is obtained by an average, usually, of station magnitude given above. Yield of a U and T is estimated using a relationship between body weight magnitude and yield when we use cyclometric method. The equation here is a simple form. The constant 4.45 is for East Kazakhstan test site of the former Soviet Union, which has the solid granite rocks. And the constant depends upon the test site conditions. For example, it is 4.25 for Novaya Zemlya test site in Russia. We need more detailed knowledge on geology of test site, burial depth of explosive that controls overburden pressure. In return, that also affect seismic wave amplitude. Groundwater table level and coupling with the surrounding medium is also an important factor. In case of North Korean test site, as shown in the photograph on the right, that nuclear tests were carried out inside Edit, whose entrance is at about 1,500 meter elevation, here known as North Portal, and the East Portal for the first one in 2006, and the Mount Top, which is about 2,200 meter high. And so the test site provides about maximum about 700 meter of overburden for the nuclear test conducted in this site. Now I'm showing you some results of our study that on the map left is showing station site effects with using the triangle with a different color coded and different size that indicate the global distribution of seismic stations with various station site effects. For these 201 stations of the IMS and global seismic network stations, you can see that there are systematic diffusion of magnitude radials or magnitude greater than average or below average. For example, Australia, Western Europe, and Eastern North America has a blue symbol here, which has a greater magnitude than those in Central Asia and Western US, which has a red triangle that we call a positive compensation. The map on the right shows the average path effect, which is a very similar pattern to that of station site effect shown on the left. The positive and negatives are almost a similar pattern, though so it's a positive corrections or positive path effect at stations in Central Asia and Western US, and negative effects at Australia and Pacific Ocean, but they are much smaller values than the station site effect. These are important findings that help us to establish reliable magnitude and the yield of the North Korean nuclear test. I think we can provide reliable estimate of the yield for the 6 underground nuclear tests conducted by North Korea, as well as any future such explosions. We had interaction with scientists at the national labs, Lawrence Livermore and Los Alamos National Lab, as well as International Data Center of CTBTO in Vienna, Austria, through the support of MTV Consortium. I think the appropriate offices in the US Department of State and Department of Defense who deal with testbed monitoring programs, research programs, will be interested in our result. We try to collaborate with folks in Korea and in South Asia and Far East Asia, but it was hard during this COVID-19 pandemic period. We opened a scientific session for nuclear testbed monitoring during 2020 AOGS annual meeting, but it was canceled just before it was about to open. In concluding our research, we obtained station side effects for 200 IMS and global seismic network stations. The station magnitude adjustment on the order of approximately 0.4 magnitude unit, which is quite substantial. Station side effect show systematic regional distribution, positive adjustment for Australia and Eastern North America, and negative adjustment for Central Asia and Western US. We obtained an average regional path effect that varies gradually from positive to negative, similar to the station side effect, but much smaller values, if not exceeding plus or minus 0.1 magnitude unit. These results will help us to establish a reliable magnitude yield relation for the 6 North Korean underground nuclear tests. Next step is that we are working on writing manuscript for publication of our results, and we would like to expand our work for more detailed analysis of test site conditions to estimate yield and validate regional scale path effects on the body wave magnitude determination. For your attention. I'll be happy to answer any of your questions.